I studied stem cell, and I did some innovation in the anti-aging. So we have a couple questions interview, and then the audience may have some questions to Professor Smoot, and we have the open Q&A sessions. So the first questions, I mean, you are the leading physicist in the world, especially for theoretical physicists and also experimental physicists. And from the perspective of physics, how do you understand the cell aging?
Right. So my history, or what I'm well known for in physics, is to study the beginning of the universe and how it developed and how we got to the point where we have galaxies and stars and planets. And of course I worry about the question about when we get light. But you have to realize that's actually pretty simple. Even though it seems very complicated and is daring to think that goes. What goes on in a cell is machinery, which is extremely complicated. Many more things go on in a cell than go on in the formation of a galaxy, even though a galaxy is pretty complex. Although there's a lot of statistical stuff that's going on. And so it's only now that we're reaching the point where we've developed the tools and the understanding that we can actually look at the machinery, what's going on in the cells, see how the proteins evolve, understand that there's information encoded on DNA or on RNA for viruses. So it wasn't surprised to me, although it was surprised to a lot of people, that the viruses, like the COVID that we just went through, mutate at a much higher rate than systems that are based on cells, which have DNA, which have much more error correcting. So you expect there to be a lot of errors in viruses compared to it. That means viruses are going to mutate quite fast. And it's amazing how much trouble nature goes to encode the information of the DNA and then actually correct that and so forth. And still there's feedback from evolution, things that make mistakes, don't survive. But the thing is, why is it the level it is? Well, it has to do with how stable the environment is and all that kind of stuff. But it also has to do with the fact that the DNA is really encoding how we make proteins. Those proteins then tell us how we take the food and turn it into things that we need to make the cells work. So there's a lot of complexity of what's going on. So like I was saying, your DNA tells you what kind of food you can tolerate, but it also needs to tell you what other kind of things are coming in the environment, what other molecules and what other cells are there. And so as a scientist, understanding what can go on, it's a more complex problem about what's going on, but in fact, science does make progress. That's one of the things that I find really good about science, is the stuff that you did. We used to say, last year's discovery, 10 years ago discovery, that was a great discovery, but it's today's calibration. Once we discover something, we can use that as something to calibrate our tools and our observing things on in order to see the next thing. We're reaching the point now where we can understand what the molecular machinery is inside of cells, and we know that in fact it depends on a lot of random processes going on and correcting itself, so that doing this medicine is difficult, but we know that a lot of the stuff is put right in the DNA, and if there are flaws in the DNA, and there are going to be flaws, I tried to calculate this. If a cell double divides, if the first fertilized cell divides and separates into two, or something, or from the earliest divides, what are the chances that two twins are identical? And the answer is actually much less than one, because there are going to be genetic errors in some of the early divisions, and they're going to have slightly different genes. Now they're going to look really much the same, but they're not. You could actually tell them apart if you really did a careful DNA analysis. So we're reaching this point where we're able to look down and see stuff on a microscopic a truly nano scale, and understand what's going on. And that makes it possible for us to think about how can we repair the machinery inside of cells and make people be healthy for a long time.
Wow. So, I mean, from high school, I studied, physics, like the thermodynamics, tell us that each system may undergo a decay along with time. So, I mean, that is no exception for the biological systems. So, biological systems are still undergoing a decay, and due to, the disorderness, something entropy, we understand that. And so like anti-aging is try to reverse the disorderness along with the time. So, the next question is, so you talk about some physics understanding for the aging, and how about to try to explore some resolution from this angle, and how you understand, from the physics, try to reverse the aging and.
I wish that it were simple like the universe, or the way we do physics. We try and do what we call reductionism, reduce it to the essence of the problem. And in biology, aging is much more complicated. There are many processes, probably 15, 16 major processes that are involved in aging. There is, cells make mistakes when they're dividing, and they get senescent, they get turned off, or they become senescent. But they contaminate the other cells around, and they disrupt the behavior. So there's the cleaning out of all the bad cells, right? There is some waste that happens between the cells. There are genetic errors. There are external viruses and things that come in. There's a huge number of things. If you want to stop aging, you've got to stop all 15 of those. But if you want to stop some major pieces of aging, you only have to stop a few of them. And if people live a lot longer, then you need to attack the next problems. So it is a much more complicated. It's not quite as complicated as solving political problems, but it is complicated to try and figure out how you're going to address that. But a lot of us have a vested interest in seeing that we solve the medical and the chemical and the physical questions about aging, because we all would like to live a healthy life and be in good shape for a very long time. And, I can tell you, life goes by too fast. There's a lot more stuff I'd like to do. I don't want to get to be old yet. But on the other hand, nobody's beat time yet, but it's a good race to get in.
Right. So something like we try to repair a 200 years old house. How can we do it? We need to restore the orderness. So in biology, we do have this kind of a technology called cell reprogramming, and to reprogram the orderness of the aged cell and back to the young stage. And then to recover and to recover. So that is a balanced perspective. And I think, in your talk, you mentioned longevity, escape velocity. So that means the lifespan for humans increase, especially increase. And 40 years ago, so the average lifespan for a human probably 60 years old, but now it increased to 80. And for our generation, so maybe increased to 90 or even 100. And so, there is some limit for the lifespan in your perspective. So definitely there's a limit. What do you think that there is the limit of?
And the example I gave of women's life expectancy in the UN reports, they had 3 different things that they thought were the limits of life expectancy that we solved in terms of health treatment. And that's why Japanese women live to be quite old, right? Because they live a good lifestyle, and they, you know, and those medical problems are done. But we know there is the issue that as cell divides, errors accumulate, and at a certain point, the cell has a mechanism to shut off the cell division, and then you have the senescent, the old cell or the dying cell. They're kind of taking up space and resources in the human body. And you would think that is one of the limitations, but in fact, we're learning some, and this is an argument I had with Elizabeth Backer, who got the Nobel Prize with her colleague for discovering the telomeres, that the telomeres are the things that turn it off, but you can, I argue with her, if you could lengthen the telomeres, people will live longer. Now yet, it's very tricky, because lengthening the telomeres makes you much more prone to cancer. So you have to be smarter about that. But now we have much better tools for measuring the DNA and so forth. But one of the things that we have seen more recently is the length of the telomeres that you have on the various DNA strands actually varies a little. They're not, they're all this length. There's some this length, some that length. And so if we're going to keep people living and to keep the cells from going, you know, so the problem with cancer cells is that they're immortal because they shut that off. You would like to be able to shut part of that off without causing cancer. And so that means you need to be correcting the errors and keeping the telomeres long. That's one of the things. And I actually had colleagues that I did an experiment with, and we got some ingredients made from China and other places. It's done through a pharmaceutical company in Germany. So but the fact is, you know, it's possible to do things to make it so that we extend what we thought was a fundamental limit, and it's the accumulation of errors. And you know, we could do that. And I say, if you kept stem cells for people, you could think about going in and doing periodic corrections to a human's, you know, DNA in each cell and keep them, you know, like the original copy.
Yeah, thanks.
That's far in the future. Yes.
Well, have you considered the limited lifespan, and so we also, I mean, our dream is kind of to be unlimited lifespan, like longevity, so like eternity. Okay, so I mean, have you considered about to extend the biological longevity, or you mentioned bio-robot combination? That is another way to increase the longevity, but it's another, is a different form of longevity, and also digital eternity. So like store your brain, your information into the cloud or something. And how would you think these three forms of longevity, from the limited longevity to unlimited?
Right. So there's nothing that's totally unlimited, because depending, if the universe still remains accelerating, eventually the energy sources available to humans or human society or intelligent society is going to run out. And that's the problem. But that's a really long scale. And the humans aren't used to thinking longer than 100 years or 1,000 years, right? So thinking billions of years, tens or hundreds of billions of years is not something that we worry about yet. But the fact is, do you think you would be the same person if you were digitally uploaded into a computer than you would be if you were uploaded into a healthy human body? Mm-hmm. And the answer is, clearly humans are not machines, and yet putting your software into a machine is not the same as having you. Mm-hmm. And so it depends on what you think is important for your idea of immortality. Not everybody wants to be immortal. Some people get tired of it, but there are a few people who like to live forever. And the rich people are probably going to get some fraction of that. They're going to get very long lives because they can afford the special treatments. I think we have to think about what it is as our goal and what's going on. And, you know, do you want to be the machine, loaded in a machine that's also got an AI that's not smart And it's a tricky kind of question. Right now, the people in this room would like their own lives and their own bodies to be healthy and long-lived. They want to be healthy, they want to be happy, they want to do what they're doing.
Yes. Okay. So we may have some open questions, and so what about this audience? One question.
Hi, Professor Smoot. I'm an AI engineer. By the way, I also studied at Berkeley during my undergrad time. I'm super curious about the Fermi paradox. And you know what? When I had my road trip to Roswell, New Mexico, I didn't see alien. And I believe that neither does Elon Musk. So, in your perspective, do you think there's maybe a possibility that will revolutionize our understanding of the universe? So, do we need a simulation?
Fermi paradox. The universe is so huge, and there must.
So this apparently happened during World War II. That when they were at Los Alamos working on building the first atomic bomb, that they had a discussion at either at lunch or so about aliens and about what's going on. And Fermi started thinking about it, and when he came down to get coffee break, he asked the question, "Where are they?" Yes. It took other people there about a week to figure out that what he meant was, if there were intelligent aliens in the universe, eventually they would spread out across the galaxy, as soon as they became spacefaring, out across the galaxy at a speed that's a good fraction of the speed of light. So why weren't they here? Right? That was the question. And so we worried about the Fermi paradox a lot away. You know, the three-body problem has one solution. There's a dark forest out there that eats up things that are too noisy. There's another thing, and when I do the calculations, and I'm old enough that I remember Francis Drake. There's a Drake equation. We filled out a lot of the Drake equation unknowns now. How many galaxies, how many stars there are that have planets, and so you could put a lot more numbers in there. There could be anywhere between one civilization, advanced civilization in the galaxy, to many thousands. That's the kind of time range that you would normally feel reasonable confidence. But it could be much broader than that. And so we might be the only intelligent race in our own galaxy. That seems unlikely, but that's a possibility. But there could be a lot more intelligent races in other galaxies, and we would never interact with them. But even if they were here, it's not clear that we would know and see. But the thing that people used to worry about is the Fermi paradox means maybe when intelligent races get to the point where we are now, you trash your environment and you all die. Right? You don't make it through that threshold to where you become interplanetary. So there are lots of things and lots of questions that come up from this problem. It seems very likely to me there's life in more places in the galaxy. The chance of advanced life is less well known, but over the whole universe, there certainly is some advanced civilizations. And how many of them died out, how quickly is another question.
Thanks. Probably due to the Bears. Probably due to the limit, we will end up here. And thank you, Professor Smoot, for coming here to enjoy your insights. Not just the longevity we talked about, but also the energy revolution and also artificial intelligence. I think all the audience enjoy all the insights, and we want to see how our time is going on and try to give the humanity to the time to make a very positive future. Okay, thank you, Professor Smoot.